Hi there, I'm Dr. Ben Britton. This is the second in the series for an overview of focused ion beam microscopy. If you haven't had a chance, please do have a look at the first lecture. It will give you an idea of how the structure of this series is working. In this lecture, we're going to focus on some of the details of how the FIB itself works. I do want to recognize that, of course, I am supported by fruitful collaborations with a range of people, and so they're listed down here. So a focused ion beam instrument is established, and the key detail is how the FIB column is working. So the FIB column looks in some ways quite similar to an electron microscope. So we basically have the source of the ions. We have the so-called ion gun that sits often at the top of the column. And then we have a series of effectively condenser lenses, gun valves, and a few other bits and pieces, as well as some apertures in the system that enable us to down select to a particular probe current. Once we've got the beam in the microscope, we can then choose whether we want to blank and send the beam off somewhere else, or we can put it on our sample when we need. And so then this beam can then, when it's behaving itself and we like it, it can be sent down the microscope, and we can go through effectively a scanning octopole that enables us to deflect the beam across the surface of our sample. And then we have basically down to the objective lens and the end of the pole piece, and then it inserts itself into the electron microscope to enable us to target this at our samples themselves. Now there are a few other bits and pieces that are useful. We have the Faraday cup that enables us to measure the probe current of the beam, and that can be especially useful when we want to understand, for instance, the ion dose that our sample receives. So the goal of our focused ion beam system is to create a focused probe of accelerated ions. The ions themselves are typically accelerated, often anywhere between 200 electron volts and say 30 kilo electron volts. The ions themselves are often positively charged, and they can be deflected in the microscope to scan across the surface of our sample and interact with the surface of our sample for our range of applications. Now, the sample itself is typically mounted on the surface of a carousel and stage, and so we might have, for instance, X, Y, Z, and R that enables us to move the sample around the chamber. So we can exchange from looking perhaps at our sample to also we could then move over and shift over to a handling grid that will enable us to pick up our nano or micron sized sample and put that in a secondary instrument. Now there is a range of extra equipment that will be used in concert with the FIB column. We're going to heavily use a scanning electron microscope and the associated analytics such as the ETD detector. We might also have a nano manipulator to move samples around, and so that's, for instance, when we're doing a lift-out operation. We're going to have a gas injection system, a GIS, that enables us to enhance etching and deposition depending on the precursor gas that's present. And I've already mentioned the value in the sample stage that's presented in the microscope. Now, the FIB itself, there are two types of flavor typically of FIBs. The first of which are typically more established, are the gallium FIBs. These are using a liquid metal ion source. And so in this system, we have a very similar setup where we have the ion source at the top. We then have the ability to extract the ions from the end of the wetted tip. So we have the extraction electrodes that then can accelerate those ions, down the primary column. And then we can have a condenser lens to shape the probe. We can steer this across a particular ion current selection aperture set. And then we can have measurement of the probe current as well as blanking of the beam in a beam blanker and Faraday cup system. And then we can have the scanning and stigmation to improve the shape and where the target beam hits our sample. And then we'll bring it into shape and to a point using the objective lens that will hit our sample. So we've got our ability to create our gallium ions. We can form the probe of those high voltage ions through the system. Once we've done that, we can select a current and typically a beam size. And then we can measure the current and stop the beam. So when we don't want to interact the beam with our sample, we can use a blanking system to move it out the way. And then we can focus and scan the beam in a very routine and automated manner. And that routine and automation enables us to really understand and use this for fabrication and manufacturing in particular. Now, if we move to a plasma source, we have a very similar setup, but we're now going to change the top of this to shift ourselves to a so-called plasma source. And we'll see what that looks like in a moment. The rest of the column looks extremely similar. I'd say one particular difference might be that you would change the ion current selection aperture, and that can be because the plasma could be more aggressive and could damage the apertures faster. So you might want a more radiation hard aperture strip for a xenon fib. The rest of this is incredibly similar in that structure. So we've now got the opportunity to run our fib depending on the particular instrument. Typically, I mentioned 200 EVs, but 1 to 30 is quite common as well. We then effectively have this in the liquid metal source. We have the ion source, the suppressor and extractor that enables us to control the ion beam off the tip. We have a divergent probe at this point, and then we go in through an entrance aperture and we condense the probe to go through the system. We have a few details that are important. The vine filter can select particular energies, so we can monochromate and control the particular ions that are going down the column. And then we can go through the system and then effectively have stigmatism and scanning octopoles and an objective lens to bring this to our sample. So we have this overall system that I mentioned a couple of times now, but one of the important aspects is that we're going to control the probe current, typically with apertures. Those apertures are often, say, molybdenum or tungsten. These are radiation hard materials that don't sputter very quickly, because all the ions that don't go down the column will interact and hopefully be quenched or stopped by the aperture itself. And again, we'll have beam deflection, raster scanning, blanking, etc. to enable us to maximize the use of the fib for the applications that we're interested in. Now, if we look at our sources, this is where there's just the subtlety of the two different source types. Let's focus on the left hand. This is the liquid metal ion source. This basically, we have a tungsten hairpin coil, and basically we have a gallium reservoir, and that gallium reservoir enables us to effectively wet the end of our tungsten hairpin. So we can basically have this wet. It forms a small, very sharp so-called Taylor cone, and as the ions are extracted by applying a high voltage through the extractor voltage here, they are pulled off the surface of the Taylor cone. Very similar to how we would effectively exploit the work function of our tungsten filaments to enable us to operate our tungsten SEM. We can do very similar. But the key trick here is that basically this wet source enables that once the ions have been removed from the Taylor cone, then new gallium can wet and drop down and form a new cone. And by controlling the operation of the extractor and the suppressor, we can basically get it that we can get a stable tip that will last us many hundreds of hours before changing the tip of our system. So that's the liquid metal ion source. We have the alternative source that enables us to form the so-called plasma. And one example that we use a lot at UBC is a xenon-based source. And in this case, we have an introduction effectively of a neutral gas. This we're going to use a noble gas like xenon. It comes in. And then inside the plasma, inside the chamber, we're going to convert that neutral gas into effectively an ion cloud. And that ion cloud can then be pulled through an extractor hole. And that's done through effectively a chamber, the plasma chamber itself in this case. Why do we use these different systems? We'll see a few things a bit later, but one of which that's important is effectively that we can look at the so-called spot size, the D50, so that's 50% of the ions will be within this size. We can do this based upon the beam current of our system. And so in this case, we see that typically for most gallium systems, there is this sort of sweet spot of a beam current between, say, maybe 100 picoamps or down to 10 picoamps, up to, say, 10 nanoamps or so. And here we get a relatively linear spot size with current domain. We notice that the spot size is typically a lot smaller for our gallium fib. That enables us to be more precise in how we cut objects as we're fibbing them. The xenon fib, this has typically a larger spot size, It's up at the sort of 10 to hundreds of nanometers, depending on how we set up the instrument. It can be made a bit smaller if we want to optimize it. But here we can effectively use xenon, and the short of this, we'll see this a bit later, but xenon, it's a large and heavy noble gas, and so it's very effective at sputtering. Gallium is effectively much lighter, and it can form effectively alloys or amalgams with certain systems, and so that's one of the reasons why you might use the two different source types here. Now you might ask yourself, well, okay, we've got these sources, why do we get the difference in the resolutions? And this is really controlled by the shape of the so-called virtual tip. So in the gallium source, we now have the Taylor cone, which is that sort of 5 to 10 nanometer wet liquid cone, and then they are emitted off with a conical probe. And we therefore produce a relatively narrow Gaussian profile. In contrast, when we have effectively our ions being propelled through our extractor optics, we have a collimated emission, but the challenge here is that the collimated emission creates quite long so-called beam tails. And those beam tails will have a significant influence, as we'll see a bit later in our different applications. So we can see this in terms of the spot size and currents. We can see this in terms of how we get different resolutions. This is a related picture to what we had. But one of the reasons why we might want to avoid gallium in our system is that gallium can collect on the interface when we prepare. This is an atomic resolution. I think it's a STEM image of a system. And so here this gallium can enrich itself, and so we get a sample preparation artifact due to the decoration of gallium at this interface. If we prepare the sample with xenon FIB, we see that we do not have that enrichment of that gallium. And so this is one example where there is an improvement because we don't have effectively sample prep induced defects in our system. There are a whole range of different reasons. We can have this very simple sort of table. This is the liquid metal ion source. This is the plasma source. We can choose, there are of course different ions, as we'll see a bit later. Gallium and xenon are the two we're describing in here. But we have basically that the gallium source, for lots of reasons, is relatively easy to focus. It alloys as it and can implant. It has a relatively long stopping distance, and that means it has controls something about the interaction volume. And it's reasonably heavy, but it has a moderate sputter yield, and so that can reduce the effective cutting rates of this system. We'll typically operate the probe in a picoamp to nanoamp domain, and that's related to effectively the resolution issues, but that gives us some beautifully fine spot sizes, so we can draw or cut with extreme precision in our samples. There are some challenges, as we've mentioned, with regards to ion implantation and alloying of our systems. The typical applications are very high precision tasks, nanopatterning and T-lamellar prep. We'll see a few of those here. The plasma FIB, in contrast, it's a bit harder to focus. Effectively, the beam is a less nice shape for us to focus. It's made of a noble gas, so it typically does not react. It may implant, and you could get, say, noble gas bubbles in here. Because it's heavy and weakly interacting, you get a relatively short stopping distance. You also get a relatively high sputter yield, and so you can cut through a lot of material quite quickly. This is enhanced because we can now go up effectively 2 orders of magnitude, and we can use the FIB with microamps of current if we want. We're limited a bit on the ultimate spatial resolution because of the shape of the probe. They're slightly different depending on your manufacturer. Those resolutions can vary. If you're not careful because of how this beam stops, you can get a relatively large amorphous layer, but there are ways to reduce the amorphous layer, the damage of that surface, but we don't have things like ion implantation or alloying really to worry about in here. Typical applications of xenon FIBs are high volume milling. One area, for instance, there is depackaging, so you want to take apart a component and look into that object. You also might want to perform tomography and cut apart a large volume of material. We'll see a few examples of that later. Now, one of the key things here in that process is that the ion beam and selecting the appropriate probe current is typically performed with an aperture. This is because it's relatively challenging to form a relatively small probe. This is related to how the Taylor cone forms and the extractor optics in the gas plasma systems. So what you tend to do is you use apertures of a series of different sizes that will control the probe current and beam size, where you can deflect the beam across different holes in a so-called aperture strip. And then once you've done that and you've used the focusing optics afterwards, you draw that onto the sample. Now, why is this important to note? Well, these apertures, this incident beam, will hit the aperture and can wear this aperture over time. So, due to ion beam milling of the aperture strip, the apertures themselves are actually consumables in a FIB-SEM instrument. And that's super important to bear in mind because, for instance, the current for a particular aperture, if the instrument is not well maintained, might drift over time. There are a series of different aperture sizes depending on the specific setup. If you want to get into this discussion, I'd suggest that you talk to your manufacturer about more details. And these are larger hole to give you more current, and they're typically made of a relatively radiation hard material, something like molybdenum or tungsten in that mix. Another important aspect of the instrument, especially for our dual beam system, is the availability of the so-called coincident point. Typically, because the FIB is interacting heavily with your surface, you don't want to spend too much time imaging the surface of your object using the FIB, because you can get ion beam damage, sputtering and removal, etc. Furthermore, you're going to use the fact that you have two beams to enable you to get a sort of three-dimensional picture of your object, and we'll see that's important for things like lift-out operations. So we have just a few key geometric points. We have where the beam, the FIB and the SEM are located, and they point at the sample. This particular point is the so-called coincident point. And that will be aligned specific to your microscope configuration. There may be very slight offsets. Ours, for instance, is set to be about 6 millimeters if the beams are well aligned, and we just do a little touch-up to make sure that happens and we understand where that coincidence sits. What we'll also do is we'll rotate the sample effectively to enable us to have the sample perpendicular to the FIB or perpendicular to the SEM, the surface of the object. And we'll use a stage to rotate. We'll typically use probably a compucentric stage rotation. Ideally, we would like this to be eucentric, so as the system rotates, effectively the object stays put. And so that's what the eucentric point is, and eucentric height is to enable that to happen. So we can optimize the point of intersection, the coincident point intersection between the electron and ion beams. We can adjust this using beam shifts. Typically, I would suggest that you want to use the SEM beam shifts to enable that to be done, because the FIB beam shifts can change a few things like the shape of the probe that will do the milling, etc. in those cases. Now, as you change so-called presets, that's like apertures or other optical controls, that beam may shift. And so it's important that you perhaps, if you're going to use multiple apertures in your experiment to mill with different currents or different voltages, then you're going to effectively align those presets to get the beam to be coincident between the different FIB settings that you've got. This eucentric point, the second aspect, is how you tilt the sample to maintain it in the field of view. Traditionally, to help you in this, you want a sample to be not too high in the chamber. That just makes your life a bit easier if you can. And this is set up that the sample, once the system is rotating the sample, that the sample stays within the field of view for this. Now this will depend a bit on the stage and sample geometry. Some of the instruments have some clever tricks to enable you to have an extra so-called M stage that can move the sample up and down to really force that eucentric to be controlled. We can use, effectively, there's a small typo, we can use compucentric rotation to compensate for those issues. When we've got the FIB, we can have a series of different use cases. We've seen this in a few places. We can do FIB-based imaging, where we use the instant FIB and we collect it with a secondary electron or secondary ion detector. And so we collect those ions or electrons, and so we can measure the total interaction with our surface. This can give us topography and Z number, and also crystallographic contrast as shown. If we introduce the FIB into our sample, we can sputter the material away, and so we can mill. To help us, we'll often put the sample at an angle to the beam, not always, but that's just what this cartoon is showing. We might also use the gas injection system, the GIS, and we might introduce a gas molecule that effectively enables us to avoid the sputtered particles from sticking back to the surface. And so in this case, we have these sputtered particles. As they get ejected from the FIB space, they get perhaps put behind the beam, and it's kind of like digging a hole on a beach. The sand can pile up next to the hole. It can make it difficult to dig deeper into the beach itself. Well, if you attach a volatile byproduct to the side of it, you can enable those things to effectively float off and not adhere back to the surface. And that's what the FIB-enhanced etching approaches enable us to do something. Slightly differently, we can switch the gas that's in the GIS system, and we can now effectively float a series of gas molecules, and those gas molecules will float around on the surface. A few of them will adsorb on the surface of our object, and then interact with the primary incident ions as well as the secondary electrons, and you can get effectively a breakdown of those gas molecules to deposit them on the surface. And this is, for instance, where we deposit a platinum-rich layer through the organic precursor breaking down on the surface of our object. Again, we'll see a bit later in the lectures how we can optimize the FIB for these different operational modes. So, what I've hopefully persuaded you so far is that we can use the FIB to image the surface of our sample, and effectively the ion beam damage and interaction, it will generate secondary ions and secondary electrons, and those two can be used to form a signal. The secondary electrons that are formed from the incident ions can be collected through a conventional ETD detector. This is the sort of SEM-SE detector. One small detail is that the incident ions can actually damage, if you're not careful, the ETD detector, and so you might have this as more of a consumable than a conventional SEM. You can also have secondary ions that are generated. Those secondary ions can be effectively collected through a secondary electron secondary ion or a SESI detector. They can also be collected through a few different cases, and those secondary ions can also be collected, for instance, through a secondary ion mass spectrometry or a SIMS system. You can have backscatter ions, and so those primary ions are returned back by the sample. That's similar to, say, BSE type imaging. And you'll also get the formation of phonons in the material. These are quantized lattice vibrations, and that will create localized heating in the sample. And we'll see in certain cases that localized heating needs to be managed with care. In addition to the two sources that we've seen so far, we can also do something clever where we can use field emission. So we can produce an atomically sharp tip. If we apply a high voltage to this tip and then have a helium or neon gas, those neon gas will then form a trimer on the surface of the tip, and then we can effectively eject that trimer and bring it down as ions through the column, and that produces a beautifully narrow beam. We get a very tiny probe size, and it's very monochromated. It typically has a reasonable brightness for our system. That's some challenges in these cases. And this is found, for instance, in the Carl Zeiss Orion NanoFab product for this particular case. Again, the FIB itself, the helium ion beam system, has our source that's just changing to this type of source on the left. But it has relatively simple and similar electron optics, as well as detectors that are in the sample chamber. Now, why would you want to change with your source types? Well, you might want to, for instance, improve your spatial resolution. So gallium FIB can produce effectively a 30 kV, has a relatively wide probe. It's high energy, so these ions go quite deep into the sample and create lots of damage and interaction. If you drop the voltage, you can make the probe smaller and interaction smaller. But if you want a really narrow and high spatial resolution, you can improve this by having that very, very narrow source, where we have the 0.35 nanometer source, that can improve the spatial resolution even further. Now, those helium ions can travel quite far into the material, and so you can actually get quite a lot of, say, transmitted or incident damage. Relatively low damage per unit ion, but there will still be a little bit of damage from the helium going into here. Helium ion imaging also has some really nice other bits and pieces to it. It has a very high depth of field because of the size of the source probe, etc. And so we can get some quite beautiful, very, very high spatial resolution images. And so this is beautiful for this looking at a diatom. This is also useful for looking at insulating and non-conductive samples. You can also look at a FinFET, so a semiconductor system with very high spatial resolution, and you can look at gold nanoparticles with, this for a scanning ion instrument is amazing resolution without having to go to the TEM in this case. There are a range of choices of what you want to do for different sources. We've seen here one example where we have effectively we've looked at gallium and xenon in some cases, depending on the source sizes, etc. But we can play with different ion types depending on how our electron column or ion column is set up. The interaction volumes will vary, but we can play with the interaction volume sizes, and that can change effectively the probing of our material and what the accessed information is. So, in this second lecture, I've hopefully provided a summary which gives you a brief understanding where we're going to focus a beam of ions. Those ions are going to interact with our material to do a variety of bits and pieces. We're going to worry about those ion beam interactions because they can give us interactions that provide signal or remove material, both of which we would like, but there may be issues associated with damaging, sputtering, and implantation that can impact our analysis. And so we have to worry about that in terms of sample preparation and a few other aspects moving forward. What we see is that there are actually a wide range of ions that can be used, although typically many systems are gallium-based FIBs. There's a sort of the next probably most popular are the sort of xenon-based plasma FIBs. And then we go towards other systems, depending on your application and where you are based for these instruments. So with that, we're going to draw module lecture 2 to a close. Our next lecture is lecture 3, where we're going to look at milling and polishing approaches for this.